Okay, so we were talking about, if that's what it says on the portal, because I think the test is on Wednesday. Okay, so we were working on page 255, number 113, yesterday. And we had, or have, a car that has some mass m that's moving initially with some velocity that's 3.20 meters per second. And what's going to happen is it's going to travel under a funnel, and the funnel is going to drop grain into the car, and the mass of the car is going to increase. And we talked about how if the mass of the car increases, what kind of force do we need so that we can keep the speed of the car the same? And we know the rate at which the mass is added to the car, right? What's the rate at which the mass is added to the car? So 540 kilograms per minute, because it's going to be something per time. Okay, so we're probably going to want to change that to what? Yeah. 1 minute divided by 60 seconds. I need to align this again so you do the math. So we get 9 kilograms per second. Probably didn't even need your calculator for it. Okay. So like we said, if there was no external force, then when we added mass to the car, which would be our event, the car would slow down because there'd be extra mass, momentum would be conserved. But from the rocket problem, we know that VREL-R is equal to MA. Right? We had that. This is a rocket problem. Whenever you have mass changing in something, it's a rocket problem. Okay? Well, it's the big M that we had in the rocket problem. So what's MA equal to? What else is MA equal to? What's MA always equal to? F net. So if we're talking about the x direction, then the only force in the x direction is going to be that applied force. And if there's a force, there's an acceleration. But it gets a little wacky because the mass is changing too, which is something that we don't usually deal with. So we can say that the applied force, at least its magnitude, is equal to VREL times R. We know what R is because we figured it out up here. We'll erase that. Oops. There we go. Okay, so the big question is, what's VREL? Well, what was VREL in the rocket problem? So it was the relative velocity between the rocket and the exhaust. Okay. And we don't need to know the positive or the negative. We don't need to know the sign because we're just looking for a magnitude here. So what's playing the role of the exhaust in this? Okay, is that what we're dropping? It's grain. It's the coal trucks that go, or the coal trains that go behind my house. Okay. So, yeah, the grain ones don't go behind my house. The grains are dropping straight down. What's the cart doing? This way, right? So if you were a grain, if you were on a grain of grain and you were going down, what would the cart look like it was doing? Moving that way. So what's the relative velocity between the grain, between the exhaust and the rocket? Yeah, it's the velocity. The only x velocity is the velocity of the train car. Because the grain has some velocity in the y direction, but we're not talking about what's happening in the y direction. We're only interested in this accumulation of mass in the railroad car and what kind of force I'm going to need to keep it moving. Okay? So that VREL, the grain doesn't have any x velocity. So the relative velocity between them is just the velocity of the railroad car. So this is going to be 3.20 meters per second times 9 kilograms per second. And what do we end up with? Which in this case, I think we could safely call a Newton. I mean, it is. And when we were dealing with this before, we weren't quite sure what to do the units as. But what I'm trying to find is the applied force. Okay? Makes sense? All right. So this is the end of chapter 9. All right. That's it. Oh, I have things for you to do for the rest of class. Never fear. All right. So we're going to stop this.